Okay, can you hear me? Does this sound good? Okay. Well, thank you for that introduction, Josh. It's nice to be here today. So I'm going to kind of walk you through an experiment that we would go through as computational social science-y or science-y people. And I'm just kind of contrast some of the differences that I see between computer science-oriented folks and some of the stuff that we do, and some potential ways in which we both can learn together. So I'm going to talk about a concept today called external reliability, which, I can give a more formal definition than this, but simply put, it really is the extent to which a specific measure in our data set can actually be generalized to mean exactly what we want it to mean. So similar to Dean's talk, this idea that we have all of these, we often have trace data, or we have algorithms performing conclusions on trace data to say whether a measure is something or it isn't something. So a way that we kind of assess that in the social sciences is this idea of external reliability, right? We actually look at the thing that the computer is coding and we say, does it actually measure what we want it to measure? This is something that I don't see enough in data science, and I'm going to talk about kind of the pitfalls of it. So if we kind of look at like a computer science-esque program or problem from maybe a Kaggle competition or something that we see out there in industry, we might have lots of features, right? And we're trying to predict something, an outcome that we're interested in. So, a good example of this is a click-through data set, which is this idea that we have ads and we're trying to predict the number of clicks that an ad gets, right? So we have the number of clicks, the outcome variable, and we have all these features that may or may not be helpful in actually getting us to that answer. So, I think that this is important to answer these kinds of questions and to build machine learning algorithms that optimize and get to the answer as best as possible. But I'm going to argue that sometimes that we shouldn't start with the machine learning algorithm. We should start with the features themselves, because good features perform better than bad features. So, walking you through a project that I'm working on now, I was working with an autism researcher in psychology, and it really started over drinks, this idea of, why are people on social media talking still to this day adamantly that vaccines cause autism? So this autism researcher in particular was, just kind of flabbergasted by this occurrence and that it's still happening on social media. So we wanted to try to investigate this question. So, we started, as most people would, by looking at keywords, right, in the Twitter data repository, and we downloaded a ton of tweets, So we put some thought into these, right? We tried to make sure we got misspellings, and we tried to make sure we got all the key-related hashtags and everything that you might expect. So after a few rounds of kind of tweaking the keywords and looking at samples, we were able to conclude that the data that we were getting was largely the data that we wanted, which was this talk around vaccines and autism. So we selected a batch and we looked at it, and I think that after, like I said, a few rounds of kind of taking words out and adding words in, we got a batch that was 98.2% accurate. So this is a small example of external reliability, but I'll show a bigger example here in a little bit. So the real key thing here that we wanted to do first in this study was not just find tweets that mentioned vaccines and autism, but we wanted those ones that mentioned vaccines and autism in a negative light, right? We wanted the people out there that said vaccines cause autism. So that's not where we stopped, that wasn't this. We had to keep going. We had to apply some type of automated learning method to kind of get this data coded in that way. So here's what we did. So we had two coders, each looking at 2,000 tweets each, and they simply just annotated whether the tweet was saying that vaccines caused autism, or that vaccines and autism were related, or that they weren't. And it took several rounds of the actual two people in a room to agree that they actually which ones were and weren't. It took very many little smaller subsamples of this to actually get a valid concept of whether a tweet was mentioning this phenomenon or not. So it wasn't just a black and white situation. There was some kind of subjective debate as to whether a tweet did mention this phenomenon. So once the two coders finally agreed, we have this concept in the social sciences called intercoder reliability. We love it. It often says that we have a concept that at least two people agree on. So we considered this data then gold standard data, and we built a machine learning algorithm on it. It's a pretty stable algorithm. It was 93% accurate, but more importantly, it had a kappa that would suggest that there was no bias in between detecting whether something was or was not an anti-vaccine tweet. So another way that I see a lot in computer science and in other areas of data science is this idea of kind of taking the data and doing automated methods to get to the same answer. So I took these tweets that mentioned vaccines and autism, and I ran it through a program called CentiStrength, which just looks at the sentiment associated with that tweet. I loaded in a specific set of training words that were tweaked to work with Twitter, that other scholars have said work well with Twitter data, and I tweaked some parameters according to lit reviews that suggested that certain parameters would perform better on Twitter data than others. So then the computer annotated all of the tweets, and it went ahead and it classified whether a tweet was negative. So I'm just kind of copying computer science method here. I didn't really do a check to see what that looked like. I just knew that it should be negative affect associated with this concept of autisms and vaccines. So, if you just kind of look at what compare the two. On the left, we have data that looks like on the left we have the gold standard data that was looked at by humans, and in general, just pulling out some examples, we saw people saying things like the CDC actually admitted vaccines can cause autism while still touting the virtues of vaccinations. Please, this is not a negative affect because there's no words here that would suggest that anything is negative, yet it is suggesting that vaccines cause autism or related. On the right, we have the sentiment approach, which is the vaccine program, corrupt A to Z, right? Clear negative affect on this tweet, saying that that vaccines are negative, and there's autism there in the handle, so it was pulled as a tweet that mentioned vaccines and autism. So we can see here that maybe there isn't one truly right answer, but these two this computer program on the right and our human data on the left are giving us two completely different concepts. So we could argue that the one on the right is actually what we want, or we could say that on the left, the human data is actually the concept that we want to be measuring. That's a subject for debate. But I just want to show you how looking and taking these two sets of tweets annotated really just change the results and a lot of important things that we're going to report as social scientists. So I want to go back to this idea of external reliability, right? This is extent to which these results can actually generalize a concept in which we're interested in. So if we're just interested in the negative affect opinions of people, then maybe the concept on the right is okay, but I think if we're actually trying to figure out when people are mentioning that vaccines cause autism, the result on the left is probably what we're really looking for. So, a common practice in the social sciences, when we actually have a computer do anything, we like to take a small subset and just verify that the computer actually did what we thought it was going to do. And that is something that I don't see as much in other areas, and I wish I would see more of it. So, after we had the machine learning algorithm go ahead and run on all 500,000 of our tweets, we just took a random sample of 350 of them and just saw that, and just verified that that annotation was exactly what we expected to see given what we had trained the computer on. And so, just under 90% of the data was what we expected. So machine learning algorithm is performing pretty well We did cross-fold validation, earlier, but we just wanted to manually just kick the tires and make sure that it actually was doing what it was. So for the non-manually annotated data, right, for that set that we use the sentiment analysis on, I'm just kind of following the black box approach that I've seen far too often and saying, I don't really know how well it did, but I know that other people have used this tool to detect sentiment in the past, and hey, they said it did a pretty good job, so I'm just going to go ahead and use it and see how it goes. So let's just do a basic comparison of what these two measures are actually let's just see how similar they are, right? They're correlated positively, but at 0.04. So lots of times it's not actually the same thing at all. So we have two completely different things, and we really need to keep in mind that if we're really interested in this concept that these measures are detecting two things. But maybe let's just say for the sake of argument that maybe the gold standard data that with the sentiment is actually more unbiased, or in some way it's more empirical. So we'll just continue on and we'll take a look. So the next part of this study that really the crux of it was using census data to kind of get these tweets then geo-resolved to micro and metro areas across the countries, figure out where these people are tweeting out so we can leverage census data to kind of look at those areas and see how they vary on demographics. So we could see if certain areas with certain demographic characteristics would be more likely to have more messages than other demographic areas. So that was the next step of the study. So we did that, and we used the census data, which worked really well. And I want to just kind of show you the first and the biggest difference that we see when comparing the two types of data. So on the left here, we have a model run on my nice humanly annotated gold standard data, right? And we have a really nice hard square here of 61%. So that's really nice. We have a lot of predictor variables in here that predicted the amount of vaccine or anti-vax tweets that we saw in geographic areas, and the model was relatively intuitive. I'll break down the results in a minute. I kind of just keep these variables. The census folks in the room will know what these variable codes mean, but everyone else will just wait a second. So the first and the biggest conclusion to me is looking at the gold standard data. The human stuff, wow, we could predict about 61% of that variance. Looking at the sentiment stuff that we don't really know if that measure is reliable, oh wow, we can only predict about 23% of that variance. So we're starting to see the value of making sure that our features in our data set are actually measuring real human concepts that we can validate, right? All of a sudden, when we know that this data is something that we can reliably measure, that humans agree on, we can explain a lot more of it. And I think that makes intuitive sense, doesn't it? So if we look at the gold standard data and the humanly coded stuff, some of the actual census characteristics look like this, right? So we have that when there is an area with more women with bachelor's degrees, that tends to be an area in which we see more anti-vax tweet behavior. That effect is further bolstered when those women are married, and that effect is strongest when women are married and also have had a birth in the last 12 months. If we compare this to the second set of data, the sentiment data, we lose the main effect. In fact, this idea that women with bachelor's degrees in an area affects the number of anti-vax talk, it just completely disappears. So that effect is no longer significant in our model. So we are actually changing the results of our study based on a key feature that we looked at in the data. So if we look at another effect here and another census characteristic that predicted anti-vax talk, we see that when women aged 40 to 44 years old had a birth in an area, the percentage or the amount of those people tended to also associate positively with the amount of anti-vax talk that we saw. So we lose that effect, and we also lose this household income effect of about $45,000 to $50,000 a year. So both of these effects that are intuitive and match a lot of research and actually could potentially be beneficial to health practitioners, we lose these effects when we use the automated method of sentiment. So, you know, I just think when we compare gold standards, it's really hard to explain. When we compare these two data sets, right, on some basic level, we could go back and we can look at these tweets and we can say, they're not that different. And in a lot of cases, you know, in looking at a small sample, I didn't see that huge of a difference. But they actually are different, and the data actually really changes. The results change drastically. So I think even just as computer science people or as data science people, where we're not often even, you know, involved in creating the features, right? We might be handed a data set where the features have already been created for us. We still need to question those features, because if our job at the end of the day is solely to explain variance or to find significant effects or build an algorithm that is optimized to perform in the best way, we still want to try to make that model as good as possible. Well, I'm telling you, it's really hard to explain variance, probably due to random error, when we're using features that are not really good features. And we really need to make sure that they are validated and that people are actually looking at them and making sure that they're externally reliable. Not only are our models not going to be as good, right? The R-squares will go down, and et cetera, et cetera. We're actually going to find that less things will predict these outcome variables, right? So we're going to find predictors not being significant just because the actual outcome variable is not as good as we want it to be. So we're also opening the door to completely spurious results, things that might come true that are just a result of the random error in the data. I didn't really investigate it for this talk, but I'm sure there are some variables that became significant because of the error in our data. So, you know, obviously outcome variables are really important, and a lot of times they're black and white. Whether someone clicks on something or they don't click on something is a black and white variable that there's no real objectivity to. We don't need a machine learning algorithm to figure out the number of times people click on an ad. But we do need to really keep in mind that all of the features that we generate to determine whether someone is clicking on an ad or not probably really depend on their external reliability. So if we know in this case that this variable or this outcome variable of anti-vax behavior is really highly dependent on how we create it, I better believe that every feature in a machine learning data set is also going to be highly dependent, or its ability to predict something is going to be highly dependent on the way that it was created, right? If it was created using automated methods and it's meant to approximate some type of human behavior, we are not going to probably see it perform as well as something that might be more thoughtfully created in using things like external reliability, checks, human checks to make sure it is what it says that it is. So, you know, I just think that, you know, asking as a data science, how are my features being created? How are these leaps being inferred, right? Like Dean talking about this trace data. How are we taking trace data and turning it into bigger concepts like gender? Or how are we using a machine learning algorithm to detect whether something is present or absent? Really important for us to understand those leaps and to make sure that human eyeballs agree that this concept is something that, you know, is happening or isn't happening when there's some type of objectivity to it. And I really think that training algorithms with human annotated data, that's not a groundbreaking thing to say, but really the human data always seems to work best when the concept is within the realm of being able to train a computer. And you know, even the most modest samples of actually pulling the results, looking at your features and making sure that they make sense, even the smallest amount of that really can tell you whether your feature that you're creating or your outcome variable that you're creating is actually what you say it is. So let's take a second to just appreciate that even if you just care about, you know, how good your model is or the number of predictors that you can use to predict something from happening, even if that's all you care about, you're an optimization person, still the quality of your features are ultimately going to dictate how successful you are, and you have to ask these questions if you really want to build the best model. So that's it, and we're going to save questions until the end.
the number of people saying they dislike something they see or hear for every second of the ad. And then the blue line is the number of people saying they like something for every second of the ad. The circles just are indicators.